Welcome, I'm Daniel Pizarro from the University of Alcalá. Today I will be presenting the tutorial Analog to Digital Conversion as a part of the work of the Ruby team in the Erasmus Plus project GEMS. I will guide you through basic concepts of analog to digital conversion and examples of conversion of multiple channels in the Ruby board. This tutorial is structured as follows. First, we will outline the objectives. Then we will cover the basic concepts related to analog to digital conversion. We will specifically look at the ADC capabilities within the Ruby module. Following that, we will walk through a two-channel audio acquisition example using the Ruby board. Finally, we will summarize with conclusions and provide references for further study. Let's define the objectives for this session. This lecture is focused on understanding the basic concepts of analog to digital, or ADC, conversion. What is it and how does it work? Specifically looking at ADC conversion using the ESP32 microcontroller, which is the core of our Ruby module, and demonstrating two-channel audio acquisition using the microphones integrated in the Ruby module. It is also important to clarify what this lecture is not focused on. We will not cover exhaustive, in-depth ADC control parameters or advanced analysis techniques. We will also not be covering high-fidelity or high-quality audio conversion, focusing instead on the fundamental principles and basic usage. Let's begin with the basic concepts. What's an ADC? Analog to digital conversion, or ADC, is the fundamental process of converting continuous analog signals like voltage or sound pressure into a discrete form that computers and microcontrollers can understand and process. Why is this important? ADC acts as a bridge, enable digital systems to interact with the real analog world. ADCs are crucial in countless applications, including audio processing, sensor reading, instrumentation, digital communications, and medical devices. We need to understand several basic concepts involved in the functioning of ADCs. First is sampling. Sampling involves measuring the analog signal's amplitude at discrete, regular intervals in time. This diagram shows a continuous signal from which we take snapshots, the red dots, at intervals defined by the sampling period. The next concept that is important is quantization. This converts the continuously variable sample values into a finite set of discrete levels, represented by digital numbers. The diagram illustrates how the sample values are mapped to the nearest available digital level, the steps in the orange line, introducing some quantization error. Another key concept related to sampling is the sampling rate. The sampling rate is simply the number of samples taken per second, and its unit is hertz. The sampling rate is computed as the inverse of the sampling period. Another important concept is the Nyquist theorem. This is a fundamental theorem that states that to accurately represent an analog signal in digital form, the sampling rate must be at least twice the highest frequency present in the original signal. Sampling below this rate leads to aliasing, where higher frequencies incorrectly appear as lower frequencies in the digitized signal, so you cannot recover the original signal anymore. To illustrate this, we show the following signal, which is a pure tone with a frequency 1 divided by t. If we sample at the sampling rate fs equal f, so the same frequency the signal has, we barely capture the wave shape. Sampling at twice the frequency, which this is the Nyquist rate, we capture the frequency because we see signals up and down, but we cannot recover the original waveform. At higher sampling rates, for instance 4 times the frequency, we have a much better representation of the original analog signal. Another key concept is resolution. Resolution of an ADC determines the number of distinct digital values it can produce to represent the analog input range. It's typically measured in bits. A 3-bit ADC, as shown here, can produce 2 to the power of 3, which is 8 discrete output values from binary 000 to 111. This corresponds to the following example. The diagram shows the continuous analog signal in blue being approximated by the quantized signal, red steps, with only 3 bits. A higher resolution, more bits, means more steps, which will result in smaller quantization levels and therefore less quantization error. Here the error is seen as the difference between the blue line, which is the original line, and the orange steps, and this leads to a more accurate digital representation of the signal. There are several common ADC architectures, each with trade-offs in speed, resolution, power consumption, and cost. Let's briefly look at there. First, we have the Successive Approximation Register Architecture, SAR. These are very popular for general-purpose applications, and they offer a good balance between moderate speed and relatively high resolution. They work by successively comparing the input voltage to fractions of the reference voltage using a binary search approach. The ESP32, which is included in our Ruby module, uses this kind of ADCs. The next architecture is the Flash ADC architecture. These are extremely fast because they use a large bank of comparators to determine the input voltage level in a single step. However, they consume significant power and typically have lower resolution compared to the other types. The final category is the Sigma Delta ADC. These are widely used in high-resolution applications, particularly audio, where speed is less critical than accuracy. They use oversampling and noise shaping techniques to achieve a very high resolution, often at lower speeds. Now let's focus on the ADC capabilities within our Ruby module. Specifically, the Ruby module contains the ESP32C3 microcontroller. This microcontroller features two built-in ADCs, and these are of the type SAR, as we saw before. It supports a maximum of 6 measurement channels. These two ADCs share the channels in the following manner. ADC1 has 5 channels, and those are connected to general-purpose pins from 0 to 4. And ADC2 has only 1 channel, connected to pin 5. For our purposes in this tutorial, we will use only the ADC1. And the maximum single-channel frequency that we can achieve with this ADC is around 80 kHz, according to the documentation, through effective multi-channel rates, though effective multi-channel rates will be lower. The ADCs offer a 12-bit conversion resolution, which means 2 to the power of 12 distinct values. An important feature here in this ADC is the attenuation factor. The ESP32 ADC input range can be adjusted using attenuation factors. By default, 0 dBs correspond to an input range that is roughly from 0 to 0.75 volts. Increasing the attenuation factor extends this range. For instance, 2.5 dBs allows up to 1 volt, 6 dBs up to 1.3 volts, and 11 dBs allows the widest range, approximately from 0 to 2.5 volts. Selecting the appropriate attenuation factor is crucial in our applications because it allows to avoid clipping the signal while maximizing the use of the ADC's resolution. The Ruby module integrates 2 microphone sensors directly onto the board. These are amplified microphones based on the MAX4466 chip. These microphones have a silence mean voltage of around 1.2 volts, which means that when there is silence, they will output 1.2 volts. The gain of the microphones can be adjusted using potentiometers on the microphone modules themselves. But for the integrated Ruby module that is shown in the slide, they are typically preset. As shown in the slide, these 2 microphones are connected to ADC1. Specifically, one microphone connects to ADC1 channel 0 and the other connects to ADC1 channel 1. Since the microphone output can exceed the default ADC range, which is 0.75 volts, and the offset, which is 1.2 volts, we need to use attenuation. In this case, the optimal attenuation factor is 11 dBs, which gives us a range between 0 and 2.5 volts and easily accommodates the range of the signal we can capture with these microphones. This will be important in the practical application that we will explain next. Let's outline the practical example that we will work with. We want to achieve a 2-channel audio acquisition using the Ruby module. The objective is to capture audio signals simultaneously from the 2 microphones, which are connected, as we said before, to ADC1, to 2 channels of ADC1, channel 0 and channel 1. We'll aim for a resolution of 12 bits and a frequency of 20 kHz per channel. Also, we will show how to visualize through the serial port the information acquired from the ADCs. In order to accomplish this, we will use the Arduino libraries and the ESP32 libraries. The screenshot shows the typical Arduino IDE. Let's break down the Arduino code for this example, starting with the initialization and setup sections, where we define the different constants and global variables that we will use in our code. We start with the conversions per pin variable that controls how many simultaneous conversions are done for each of the channels and each of the pins. In our example, we want just 1 conversion per pin. ADC pins specifies the pins connected to the ADC channels we want to read. Here 10 corresponds to channel 1 and channel 0. The next is the number of samples that we want to collect from each channel before processing or displaying the information. Finally, sleft and sright are integer arrays to store the raw digital sample value from the channels. Next, the setup function configures the system when the ESP32 starts. Serial communication is initialized with the function serial begin. Then we set the resolution of the ADC to 12 bits, its attenuation factor, and also the frequency, which is 20 kHz times 2 channels, which is equivalent to 40 kHz one channel. We also start the continuous ADC conversions because we want to work with the continuous mode of the ADC in the ESP32. Now let's examine the main processing logic, which typically runs in the loop function. First, we have the ICR flag check. The code continuously checks if the ADC conversion flag is true. If it is true, it means that a new buffer of ADC data is available from the DMA. The flag is immediately set back to false after this is true. Next, we have data reading and storage. In this case, we fill the buffer, and if successful, the code extracts the average millivolt reading from each channel and stores these values into the sleft and sright arrays. The sample counter n is incremented if reading fails, an error message is printed. Stop, print, and restart. Once the desired number of samples, controlled by n samples variable, has been collected, the collected samples are printed through the serial port. A loop iterates through the sleft and sright arrays, printing each pair of samples on a new line, separated by a comma. This format is suitable for the Arduino serial plotter. The same counter n is reset to 0. Finally, we add a 1 second delay, and simply to slow down the output rate for better readability on the plotter or terminal. To visualize the acquired data, an experiment was performed. A 1 kHz pure tone audio source was directed towards the Ruby board microphones. The Arduino serial plotter was used to receive the signal. In this case, this plot clearly shows two-channel acquisition of this 1 kHz sine wave. We can observe the waveform captured from both microphones, which is very similar to a sine function. If we count the number of samples between two consecutive minima of the signal, we can see that it's exactly equal to 20 samples. This corresponds to 1 kHz sampled at 20 kHz. And also the plot shows the values in millivolts directly. Let's summarize the key conclusions from this tutorial. Analog to digital converters are essential components that allow digital systems like microcontrollers to capture and process real-world analog signals. The ESP32 microcontroller on the Ruby module provides powerful ADC capabilities, featuring 2 built-in ADCs, and we can configure resolution and attenuation factors. The 2 microphone sensors that we have in the Ruby module are conveniently connected to 2 input channels, and we can do simultaneous channel acquisition from these 2 microphones. This tutorial demonstrated with a practical code example how to do this on the ESP32 in the Ruby module, and how to send the resulting signal through the serial port. For further details and documentation, you can refer to these sources of information. Also check the further reading material that is available in this course. Thank you for watching. This video was created by the University of Alcalá for the GEMS Erasmus Plus project. This is a collaboration between the University of Ljubljana, University of Alcalá Teaching Factory Competence Center, and the Delft University of Technology. It is released under Creative Commons Attribution and is funded by the European Union.